Hello guys, welcome back to Maison African Motives, still on industrial electronics and for working on revisions that is on the AC theory. We have got the question paper of August 2021 that you're going to focus on. Question number 2, where we are given 2.1 to explain how the Q factor affects the bandwidth with the aid of a characteristic curve. So we are asked in this case to apply a characteristic curve in our explanation on how the bandwidth is going to affect. So here we are given our characteristic curve, then an increase in a Q factor will result in a decrease in the bandwidth. So if we increase the quality factor, the bandwidth is going to decrease. High values of inductance and low values of capacitance will then produce a high Q and a low bandwidth in this case. So these are the this is how we can have it in words, as we can see from our diagram, having our current in the amplitude of the current, which is our current in amperes, then also the frequency and the resonant frequency that is in between at the peak here. That is where we've got our resonant frequency, and also to label that here our inductive reactance is greater than the capacitive reactance. On this side, our capacitive reactance is greater than the inductive reactance. All right, so this is our diagram and explanation that we need. Then the second part, which is all right, which is actually a lot, but let's see how we can attempt this question. We are given study the circuit diagram below and calculate the current flowing across the resistor R3 using J notation. All right, so we are asked in this case to apply or to use the J notation in this case. How can we answer this question? All right, so let's see what we have here. Okay, let me just have another marker here. All right, so we are supposed to apply the J notation in this case, but how is that possible? How can we apply our J notation in this case? That is our question. So considering our J notation, what we need also is to locate our resistor R3 in this case. All right, so where are we having our resistor R3 that is across here? That is where we have our resistor R3s. This is where we are having resistor R3. So if you are to check properly from your diagram, if this is where we have our resistor R3 here, the current that flows across R3 in this case, all right, we are given in this case, let's say this is the flow of current. We are going to see that this current is actually the current that is from the supply. So the current from the supply is the same as the current that is going to flow across the inductor. It is the same as the current that is going to flow across the resistor R3, since these are in series. This current is going to branch into these two that is in this parallel circuit. Then these two goes back again, add together, we have got our total current. So meaning to say the current across R3, which I can refer as current IR3, is equivalent to the supply. It is the same as the supply current. So current across resistor R3 ohms, or just resistor R3, like given here, R3, not ohms, but R3, is going to be equal to the total as the current across, the total current of the whole circuit in this case. So that is what we can see from this concept. So meaning to say, our question is simply to calculate the total current, because we have seen that it is the same, because this is just in series. So if it is the case, how do we calculate the total current? We know that our total current must be equal to the total voltage, which is our VRMS in this case. So we are referring to the total voltage over the total impedance in this case. So what we are supposed to do is to find the total impedance in this case. All right, so let's check what do we have in this case. All right, in between here we are given Z1 and we are given Z2 and we've got Z3. So we are going to combine these, all right? So we are going to combine these to find Z1, Z2, Z3, so that we can find our total impedance in this case. So starting with Z1, let us check what is happening across these 2 points from this point through the capacitor 1, the resistor R2 in this case. These two are in series. So meaning to say our Z1 is going to be equal to, all right, in actual sense, our ZT is supposed to be, since Z1 and Z, let me explain this first. Z1 and Z2, they are in parallel, and Z3 in series to these two, meaning to say our total impedance was supposed to be taken as product over sum of Z1 and Z2 over that is product over the sum Z1 plus Z2, then plus Z3 in series. So meaning to say what we need is to combine to find Z1, to find Z2, to find Z3. All right, so this is what I'm trying to say. So Z1 now, if we check the combination that we have here, we have got a resistor and a capacitor. So a resistor and a capacitor, to find Z, we are going to use the formula Z is equal to R minus JXC. In if you're dealing with a capacitor. If you are using an inductor, it is going to be plus XL. All right, where we know that XC is simply from the capacitance, that is 1 over 2 pi FC. So we are going to find XC from there. So we have the resistance and we've got the capacitance. So we are going to find XC first, which is XC when our capacitance is 145 microfarads. So we can calculate XC first here. So XC is going to be 1 over 2 pi times the frequency from our circuit. Here our frequency is given as 50 hertz. So the units for frequency is measured in hertz. So that's your frequency. So we are going to multiply by the frequency 50 hertz. Remember our capacitance was 145 microfarads, and micro, that's times 10 to the exponent of -6. So we can obtain the value of XC in this case. So to 3 decimal places, we are going to obtain something like 21,952 ohms in this case. So this is our XC, the one that we need here. Remember, we are supposed to use complex numbers, that is the J notation. So we are now going to find Z1, where we said there is a capacitor, so it's going to be minus JXC. So we use the resistance that is in this connection. From this point to this point, there's a resistor R2, which is going to be 101. So this is 101. So R2 is given in this case as 101 minus J XC, which is our capacitive reactance, which we got as 21,952, which is measured in ohms in this case. All right. So this is what you're going to have. And since we are to calculate certain values and we do not know what is best there, so it is best for you to actually convert also this to polar form, because as you can see, we are going to divide, and whenever you are working with the division, it is best for us to work in polar form. So that it means it is best for us to convert this value that we are given in a Cartesian or in a rectangular form to a value in a polar form. All right, so in polar form, we can simply use our calculator. So let me show you how we can use our calculator here. So this is what you're going to have from your calculator. You want to change to polar form in this case. So on your calculator, you're going to use this shift then to polar form, where it is written on this plus here. So it's a shift, then you use pole in this case, which is written a plus. So it is now in polar form. So what you're going to do, you press these values. The first one is 101. So we're going to have 101 separated. So you separate this by this comma. So there's a comma here that we see that can separate our values. All right. So, okay, I'm checking for that comma here. It's now on this calculator. It's complicated. All right. So I'm going to use this shift comma here. There's a comma. So take note, there is this one. This comma is for separating values, this one, okay? Or on this dot here. So you use this one on this bracket here. So it's shift, that comma there separates. Then you press this one as it is with a negative, this negative as it is. So it's negative 21 comma 952, like this. You close your bracket. So this gives you answer in polar form. Remember, an answer in polar form is supposed to be written as Z is given as R angle of theta, like this. So what you're going to have is the resultant and the argument on your calculator. So on your calculator here, if you check on your calculator, we have got R in this case, which is our argument. So it is already given, our R in this case. So you round off to 3 decimal places. That is going to be 103, 358. So that's 103, 358, like this. Also on your calculator, we need theta. So theta is also given. If you move this comma, if you move this arrow here aside, you move this arrow, it gives you the value of theta. So you move until you see your theta properly, like this. So this is our theta, which is negative 12,252 and so on, 262 and so on. So to 3 decimal place, that's negative 12,262. So we are going to have angle negative 12,262 degrees. All right. So this is our Z, which is our Z1 in polar form. So we've got two formats in this case that we have expressed our Z. So we do not know what we are going to have later on. So it's best for us to have this in two formats, in polar form, that is in polar form, and also in rectangular form. So this is our rectangular form. All right. So this is our Z1. So remember, like I said, we need Z1, Z2, and Z3. So we are going to move on to Z2. Let us analyze what is happening on Z2. On Z2, we are given this time there is an inductor, a capacitor, and a resistor. So we've got an RLC circuit. So on an RLC circuit, what you need to do is to compare. All right, so let me use this way so that we can properly see on this day, on this part here. What you need is to compare between the XL and the XC that you're going to have, because our Z2 can be given as R plus, depending what you're given, it can be R plus JXL minus XC, like this, provided that our XL in this case, provided that our XL in this case is greater than XC. Or we can have a condition where our Z is given as R minus J into XC minus XL, like this, provided that our XC is greater than XL. So we have to compare so that we are going to see which formula are we going to use to find our Z2 in this case. All right, so that means we are supposed to determine the XL and the XC so that we can compare the two. All right, so that is what you're going to have from this part. So remember that XL can be obtained from the inductor that we have, so we can determine our XL. All right, so let me just have it here. So XL is equivalent to 2 pi FL, which is equivalent to 2 pi times the frequency, our frequency of 50 hertz in this case, times the inductance, which is 203 times 10 to the exponent of -3. That is millihenries in this case. So we are going to obtain XL. All right, so from our calculator, if we simplify properly our XL, we are going to obtain 63,774 ohms in this case. All right, so we do the same thing for XC. We calculate our XC. So let us just have our XC here. Remembering our formula, we used this formula before for XC. We said it's 1 over 2 pi FC. So we are going to substitute and compare our values. So that's 1 over 2 pi times the frequency, which is still at 50 hertz, times the capacitance now, which is your capacitance here is 306 microfarads. So micro that's times 10 to the exponent of negative 6. So we are going to have 306 times 10 to the exponent of negative 6. All right. So this gives us the value of XC. So from your calculator, if we simplify properly our XC, we are going to obtain something like 10,402 ohms. That is to 3 decimal places. So like I said, you have to compare between these values so that you know which formula to use between XL and XC. Compare which one is bigger between these two. As we can see, our XL is bigger than XC. So meaning to say we are going to consider this part that XL is greater than XC. So the formula for Z that we are going to take, meaning to say our Z2 is going to be R plus JXL. We are going to use this formula. If it was that XC is greater than XL, you use this formula. All right. So our resistance, we've got the resistance here, which is 65. So we are going to have 65 plus J into XL minus XC. So we are going to subtract our XL, that is 63,774 minus XC, which is 10,402. All right, so this is going to give us Z2. So 65 cannot be combined to this value, so it is going to remain as it is, plus J. You combine these two inside, so we are going to obtain something like 53,372. So this is what we have, guys, for our Z2 in a rectangular form. So this is in rectangular form. So like I said, what you need is to convert, because you do not know what you're going to have later on. All right, so what you need is to convert. Let me just write our Z2 here so that we are going to simply apply it later on. So remember, we got our Z2 in this case as 65. That was 65 plus J, 53, 372. So like I said, we can have this also in polar form. So this is in rectangular form. So we can also convert this to polar form. So let us convert to polar form. Remember what I said, in polar form, our Z is given as R theta, where we've got the resultant and the argument. So on your calculator, we can convert this to polar form direct. So like I said, this is going to be, okay, on our calculator, we are going to have shift to polar form. We press this 65, shift, comma, 53, comma, so the 53, comma, this one on 53, this one on 53, use this comma, the normal comma that you use, all right? That's 372. All right, then is equal to, our answer is in polar form. Like I said, we have got R in this case, which is R is equal to 84, 105 to 3 decimal places. So that's 84, 105. Angle of theta. So from the same part, we have got theta. Just move your calculator here. Our theta is 39,3896. So the 6 changes this 9, gives us a 0 here. We are going to have a 9, so it's going to be 39. So it's going to be 39,39. So this will be 39,39 degrees. Okay, so this is in polar form. So this is best for you to just have these values in these two formats, the rectangular and the polar form. So we've got Z2 in this case. All right, so we move on. We need to find Z3. We are left with the Z3 so that we can finalize our ZT from this formula. So Z3, let us check what we have on Z3. So to find Z3, it's being affected by these two here, just the resistor. This is part of our diagram here, the resistor and the inductor. So when we are given a resistor and an inductor, how do we find Z? All right, so let me just use this space here. So our Z3 is going to be equal to, that will be R plus. So in order for you to find, it is going to be R plus JXL. All right, okay, let me just calculate. We will see later on. R plus This is an inductor, so it is going to be R plus JXL. Remember I said for a capacitor, it's minus. So meaning we need to calculate XL, and I told you guys the formula that XL is equivalent to 2 pi FL. So that will be XL is equal to 2 pi times the frequency. Remember our frequency is 50 times the inductance, which is 280 times 10 to the exponent of minus 3. It's in millihenries. So this is going to give us 68,487, which is measured in ohms in this case. All right. So meaning to say our Z3 is going to be R, in this case, our resistance. That is 81. So our resistance in this case is going to be 81 plus J 68,487. This is what we have in a rectangular form. All right, so that is our Z3 in this case. We're going to take this to these values so that we can properly see our values together here. All right, so let me just write our information for Z3. So we said our Z3 in rectangular form, we got 81 plus J 68. That was 68,487. That is 487 in this case. All right, so that is what we got in ohms in this case. All right, so these values, they are in ohms. All right, so like I said, it's best for us to convert this to polar form. So to polar form, back on our calculator, so we're going to do the same thing, just like previously in this case. All right, so let's see what you're going to have. Maybe we're going to need this, so we do not know. So that's shift, you convert to polar form. That is pole in this case here, 81 comma, that is use this comma here, that is 68 comma 487. All right, like this. So this is going to be our R, which is 106,073, 106,073, 106,073. Then we find our theta, which is here. That's 40,215, 40,215. So we're going to have theta 40,215 in degrees. All right, so this is what you're going to have. So in this case, we have determined Z3 both in rectangular and in polar form. So it is best now to find our ZT. We have Z1, we have got Z2, we have got Z3. So on our formula, we said here, we need to remember what we need, guys. We need to find the total current, which is equal to the current across the resistor R3. But we said we need the total impedance, and our total impedance is taken from the product over sum, because we said here these two are in parallel, Z1 and Z2 are in parallel. So what we can do is to find Z1, Z2 first, to find the resultant of this parallel combination. Remember, in parallel, it's product over sum. All right, so let us find the parallel combination of these two, that is Z1 and Z2 first. All right, so we are going to find the parallel combination. So for the parallel combination, we said Z1 and Z2 are in parallel. So it is going to be product over sum. So using our product over sum, that is ZP is going to be Z1 by Z2 over Z1 plus Z2. All right. Whenever you are dealing with a product, let me explain this way. Whenever you are dealing with a product, it's best for us to apply in polar form. That is the best way for us to use or to simplify complex numbers, which are in if you are dealing with complex numbers, it's best for you when you are dealing with a product to apply in polar form, even a division in polar form. Then for addition and subtraction, it's best for you to have this in rectangular form. So it is best for us to have this in rectangular form. Please take note, it's best for us to have this in rectangular form. So meaning to say, that is the idea, what I was saying, use both in rectangular and Cartesian, so that when you are simplifying, you do not have challenges. All right. So remember our Z1 here, we've got both in rectangular and in polar form. So we are going to have our ZP, which is equal to, so like I said, it's best for us to multiply in polar form. So we are going to take Z1 in polar form. So our Z1 in polar form, that's 103, 358 angle negative 12,262 degrees. All right, multiplied to, so this part here is going to be multiplied to Z2. Z2 also in polar form. Remember our Z2 here in polar form, we've got Z2 in rectangular and also in polar form, which is 84,105. That's 84,105 angle of 39,39 degrees, like this. All right. Then we divide to Z1 plus Z2. That is the product over the sum. All right. So we've got product over sum. And like I said, for the sum, it is best to use this in rectangular form. So we are going to take Z1 in rectangular form. Our Z1 in rectangular form is 101 minus J 21,952. So this is what we have in rectangular form, plus Z2. So we're going to add our Z2 in this case. Our Z2 again in rectangular form. Our Z2 in rectangular form is 65 plus J 53,372. So this is the one that we are going to take in rectangular form. So we are going to take plus 65 plus J 53,372, like this. All right, so this is for the parallel combination. Why is it it's best for us to multiply this in polar form? Because if you multiply in a polar form, you're going to use this concept. If you multiply R1 theta 1 to R2 theta 2. So actually, I'm going to have this video on working on complex numbers as a separate part, so that you just understand the basics. All right. So if you multiply in a polar form like this, what you simply do is you multiply the resultant together, that is R1 times R2. Then the angles, you add them, that's theta 1 plus theta 2. So meaning to say here, we are going to multiply, this is our R1, this is our R2. So we multiply these two. All right. So if we multiply these two, we are going to obtain 8,692,925 angle of. Then for the angle, this one we said we are going to add theta 1 plus theta 2. This is our theta 1. This is our theta 2. So we add negative 12,262 plus 39,9. So if we add these two angles, we are going to obtain 27,128 degrees. All right. Everything over this part. All right, in rectangular form, when you are adding, this is because here we are adding. So if you add in rectangular form, you add the real terms together. So we add these real terms, the terms without a J. These are your real terms. So you add 101 and 65. That's your real terms, which is going to give us 166. Then you add the imaginary part together, the one that consists of a J. So this is negative 21,952 plus 53,372. So if we add these two, we are going to obtain a positive. That's positive J 31,42 in this case. All right, so this is what we have. But as you can see, our ZP is not in simplest form. So what is it that we can do? Okay, this is a division. Like I said, multiplication and division, it's best for us to work these in a polar form. So meaning to say, we have got no option than to convert this part in a rectangular form to polar form, because already the numerator here is in polar form. So we are going to convert so that we can simplify properly. So this is going to be 8692,925 angle of 27,128 degrees. So this part, there's nothing that we are going to do because it's already in polar form. So we're going to leave this as it is in a polar form. All right. But like I said, division, it's best for us to have a division in polar form. So meaning to say we are forced to convert this part to a polar form. So let us convert this to polar form. All right. So like I said, from your calculator, we can convert this to polar form in this case. All right, so let us get to our calculator. So let me show you the part of another screen. All right, so this is what we have. So we want to convert 166. So like I said, it's shift to polar form, shift to pole, which is a plus here. That's 166 separated by 31 comma, that's 31,42 like this. Close your bracket. We've got our answer in polar form. Remember, we've got R in polar form, which is 168,947. So we are going to obtain 168,947, 168,947. All right, so that's 947. All right, just to save after some time. So that's 47. Angle of, we need the angle now. So in this case, if you check, our angle theta is 10,7179. 9 is going to change this 7 into 8. So that will be 78. So that's 10,718 degrees in this case. All right. So this is the best for us to have in a polar form. Why it is best for us to divide in polar form? Because if you are dividing R1 angle of theta 1 over R2 angle of theta 2 like this, you divide the resultants together, R1 and R2 together. So this is going to be equal to R1 over R2. The angles theta 1 and theta 2, you subtract. That's theta 1 minus theta 2. So this is the concept on how to answer when you are dividing. So that's why I said it's best for us to convert to polar form. So meaning to say here, we are going to apply this concept to say we are dividing. So we are going to divide these, our resultants together, this part. So if we divide this part, our ZP is going to be equivalent to this part is going to give us 51,454. Then angle of the angles, you subtract theta 1 minus theta 2, you subtract your angles. So these are your angles. You're going to subtract, that is 27,128 minus 10,718. If we subtract these two angles, we are going to obtain 16,41 degrees. All right, so this is our ZP, not the total, but the parallel combination, which is measured in ohms. And this is in polar form. Like I said, each and every part that you work with, try by all means to have it in both formats, polar format and rectangular format. So meaning to say, we are going to convert our ZP also to a polar format, to a rectangular format. All right, so let me have it this way. All right, so this is measured in ohms. So we are going to convert this to a rectangular format this time. So to rectangular format, okay, let me show you on your calculator. This is what you're going to do. This time you want to convert to rectangular form, where in rectangular form, we know that a complex number is written as A plus or minus JB like this, where we've got a real term and the imaginary term. So this is what you expect to have on your calculator. So this is what you do. This time you convert to rectangular. So it's shift to rectangular, where it's written rec here on minus, shift rec like this, it's right to rectangular form. So that is you use these values as it is 51,454 like this. Then you separate, always to separate these two, you use this comma here on this one. So it's a shift to separate a comma like this, which is a 16,41 like this. You close your bracket. So this gives you X and Y. So here I use A and B, but it's actually X and Y from your calculator, which is one and the same thing. So this is your X and this is your Y. So in this case, if you check from your calculator, our X, it's 49,35800, which is 358. So that's 49,358. Then we check, is it going to be a plus or a minus? All right, so let us check here. What are we having on our calculator for the value of Y? So Y here carries a positive. So that's plus 14,536. So it's plus 14,536 like this. All right. So remember that this is supposed to have a J. This is rectangular form, so there is a J in this case. All right. So we have the two formats for the parallel combination that we got. That is the total. I mean, for the parallel combination. So let us check what are we left with now to find the total or impedance. All right. So this is what we have here. All right. So like I said, from our formula. Okay, where's that formula here? Our total impedance here is going to be equal to the product over sum, which is Z1 by Z2, which is the one that we got here. Okay, let me use this one. That is our ZT. So this part is the one that we are calculating, the Z1 by Z2 over Z1 plus Z2. This is our ZP, which is the product over the sum. So we've got product over sum, we got this. So meaning to say, to find ZT, we are going to add Z3 to our ZP in this case, which is our parallel combination. All right. So let me have it this side. So I'm saying from this part here, okay, let me reduce again to this point. All right. I hope you understand me, guys. Let me rewrite this. All right. So I'm going to rewrite this on this part here. So what I'm saying is that our ZT is supposed to be equal to ZP plus Z3 in this case, from product over sum of Z1, Z2 over Z1 plus Z2 that we calculated. So we calculated this part. This is the one that we had here, our parallel combination. So when we calculated, if you check now, what is best, you are adding in this case. So addition, like I said, whenever I talk about addition, it's best for you to add in rectangular form. So you are going to use these in rectangular form. Your parallel combination, which is your ZP, our parallel combination. Remember, we've got two answers here, in rectangular and in polar form. So this is what we have, our ZP. So you're going to take this one in rectangular form, this one, that is 49,358. This part, that is the one that you're going to take. All right. So this is the one that you're going to take in rectangular form. Take note, because we are adding. That's why we are supposed to use addition. That is why you're supposed to use rectangular form. So our ZP was 49,358. So that was 358 plus J14, 536. All right. Then we add Z3 plus Z3. So if we check our Z3, we also have our Z3 in two formats. We expressed our Z3 both in rectangular and polar form. This is our Z3 here. So we are going to take this one in rectangular form, which is 81 plus 68, so this is the one that we are going to use. All right. So meaning to say, we are going to add our Z3. Remember your Z3 is 681. That was 81 plus J 68, 487. All right, so this gives us the total impedance, whereby I said addition, you simply add the real terms, the terms without a J. So this is going to give us 130,358. Then you add the imaginary terms, the part that has got a J. So this is plus 14,536 plus 68,487. So if we add these two, we are going to obtain something like a plus J 83,023, which is measured in ohms. So this is our total impedance. Like I said, everything must be written in both formats. We do not know what's going to happen. So it's best for you to change also to polar form. Remember, guys, how you change your polar form, recall to polar form. And so if we change this to polar form, you are going to obtain something like 154,551 angle of 32,492 degrees. All right. So these are the values of the total impedance that we are going to obtain in both formats, that is in rectangular and in polar form. Now the question is, with this total impedance, our question is to calculate the total current. Okay, remember, this is what we had here. All right, I wrote our formula that our total current is the total voltage over the total impedance. And this total current is the one that represents the current across the R3 resistor, because we said this is in series combination. So we are going to take the total voltage, which is 230, at an angle of 0 degrees. Take note, the angle here is at 0 degrees. So that's 230 at 0 degrees. All right. So that's our total voltage in this case. All right. So let us use our ZT to find IT in this case. All right. So from this ZT that we have the total impedance, our total current, which is the current across R3, is going to be equal to the total voltage over the total impedance in this case. And our total voltage, it was 230 at an angle of 0 degrees. All right. Divided to the total impedance, this one that we got. Division, it's best for you to divide in polar form. I say this always. If you are dividing, it's best to use in polar form. So you're going to use this one, which is 154. All right. Okay, that will be 154, 551, angle of 32, 492 degrees. All right. So this is what we are going to use as our total current, which is equal to the current across the resistor R3. So if you divide, remember in polar form, I said you divide the resultants together. These two, you divide them. So if you divide 230 to 154,551, you're going to obtain 1,488. Angle of, for the angles, you subtract. So it's 0 minus 32, which is going to be minus 32, 492 degrees. Okay, so this is our current, which is measured in amps. So this is our final answer, guys. There's no need for us to convert this to rectangular. If you want, you can convert your answer to rectangular form, but on that part where I was saying you are supposed to have your everything, you are supposed to write everything in polar and rectangle, it was because you were still calculating. But when you've got your final answer like this, why do you worry to convert this to rectangular form? Yes, you can do that, but already that is what we have. So that was our question, guys, on how to calculate the current across the resistor R3 using the J notation. So you have to revise your complex numbers. Make sure that you watch the videos on mathematics on info on complex numbers, so that you just have an idea of what exactly are we talking about. But that is, guys, from Mason African Motives. Till we meet again.